Um,
I mean, electron affinity is when an atom, it's the energy that is released or absorbed when an atom gains electrons. When an So that's in the energetics notes, TK. If you go through that, you'll find this. When an atom, gaseous, so it's supposed to be, I mean, a gaseous atom gains, let me correct this, when 1 mole of gaseous atoms, they gain 1 mole of electrons. To form 1 mole of -1 ions, gaseous ions. So it's like the opposite of ionization energy. What happens is that so it's kind of the opposite of ionization energy. Like you've got Cl gaseous and it gains 1 electron and it forms Cl -1. So whatever energy that's released or absorbed, we don't know what happens. Some energy might be released or absorbed when an atom gains electrons. So that is known as the electron affinity. I was looking for the proper marking scheme definition for this. This is question number 3, right? So, part 1. Just 1 second. So 1 mole of electrons, 1 mole of gaseous atoms. So basically, gained by 1 mole of gaseous atoms. That's about it. So it's the energy change or energy released or absorbed when 1 mole of electrons. So it's the same definition. Is that clear? This thing.
yes, sir.
Now the other thing is, let me talk a bit more about electron affinity because the next part would probably be about this. The first electron affinity of an atom is usually exothermic. So if I have oxygen gaseous atom usually gains 2 electrons, but that's the first electron affinity. It turns into oxygen -1 gaseous ion. Then the oxygen -1 gaseous ion gains another electron and turns into oxygen -2 gaseous ion. So usually it's just 2 electron affinities, right? The first one and the second one. Is that clear?
Yes, sir.
So he's saying, and similarly, if you have nitrogen, it's going to have 3 electron affinity because it forms the -3 ion. Now, what he's stating is that the first one is exo and the rest are all endo. And that is pretty much applicable to all atoms and their electron affinities. Nitrogen gains 1 electron, becomes N-1. Then this N-1 gains 1 electron, becomes N-2. Then this, since it's in group 5, so it's going to gain 3 electrons. N-2 gains another electron and it becomes N-3, right? All of them are gaseous. Now, the first one, so all of them are gaseous. Now, the first one is exo. The rest are all endo. So the question is about why is that? Why are the other ones endo? So the thing is, nitrogen likes to gain electrons. Like, look at nitrogen atom. It has a very strong attraction for electrons. It's got a lot of protons in its nucleus and it strongly attracts the electron. So all the work done is by the atom itself. So hence it's exo. It doesn't need energy. Is that clear?
Yes, sir.
But what happens after that? After that, when it gains the first electron, nitrogen becomes a negative ion. So if it becomes a negative ion, then it would be a lot harder for it to gain electrons, right? Because what do negative ions do? What do? They repel electrons, right? Is that clear?
Yes, sir. Yes, sir.
So they're going to repel electrons. So it would be kind of really hard to gain electrons. You would have to make the electron very energetic so that it can overcome the force of repulsion. So there's going to be a lot of repulsion after that. So a lot of energy would be needed. You would have to give this electron a lot of kinetic energy so that it can overcome the force of repulsion that is exerted by the negative N-1 ion. The third electron affinity would be even more endothermic. Why? Because there's going to be even more repulsion because now nitrogen has got a charge of -2. Is that clear?
Yes, sir.
So whereas the second one is endothermic. So what you're going to state over here is that the negative ion repels electron. Hence, it's endothermic. And the neutral atom, it actually attracts electrons. Neutral atom, which is also very electronegative, which means that they have a very strong attraction for electrons. They instead attract electrons. Since for the neutral atom it's exothermic, for the negative ion it's endothermic. We'll just check with the marking scheme answer, like how did they phrase this. So they're just talking about the repulsion between the electron and the negative ion. That's it. So we did talk about that. Next question is this one. Describe the general trend in the first electron affinities of Cl, Br, and I. So is this clear? Question number 2, part 2, right?
Yes, sir.
So now we have to talk about the trend of electron affinities of Cl, Br, and I. They're trying to gain electrons, right? Now, who's going to attract electrons very strongly out of the three?
Um, s-
Is it going to be Cl or is it going to
I think, is it BR?
be out of the three?
Oh,
Smaller atoms.
PL?
So smaller atoms, do they attract electrons, or bigger atoms, do they attract electrons strongly?
Smaller atoms.
So there's stronger attraction, right?
Yes, sir.
Which means it's going to be more exo, the first one. So there's going to be a very strong attraction for electrons and all the work done. So there's going to be it's going to do all the work very strongly. So it's going to be very exothermic. Iodine is a bigger atom and it's strongly shielded. So, which is why it's not going to attract electrons very strongly. So there is weaker attraction, and hence it's going to be less exo. This one was the previous one. So hence it's going to be less exo. So remember this. Down the group, the electron affinity decreases. And you can talk about the shielding effect, that Cl is less shielded, so stronger attraction. Iodine is more shielded, so hence more attraction. Not sure if they're talking about shielding electrons or trauma. I mean, they're talking. They did give marks for shielding. So and less attraction. So you had to write about shielding as well. Is that clear?
Yes, sir.
Now, here's a question on Born-Haber cycle. Calculate the first electron affinity. Use relevant data from the table 3.1 in your working. It may be helpful to draw a labeled energy cycle. And specifically, based on the data that's given, enthalpy change of sublimation of iodine, etc., all of that stuff that's given. So you usually end up drawing a Born. Did we do Born-Haber cycles? Asina, did we do this one?
But yes, sir. I mean, I've studied about it.
Okay, so briefly speaking, Born-Haber cycle is for an ionic compound. Like you've got zinc iodide over here, right? So how is zinc iodide formed solid? It's formed when zinc and iodine react, right? So zinc plus iodine. So zinc is a solid, and iodine is also a solid at room temperature. So what you do is you take zinc and you take some iodine, which is solid, and you react them together and you get zinc iodide, which is an ionic lattice, right? This enthalpy change is known as enthalpy change of formation of zinc iodide, because 1 mole of zinc, 1 mole of this is formed from its constituent elements, right? Is that clear?
Yes, sir.
So that's the enthalpy of formation. Now, what are the steps that are involved? You're going to create another path. That's what the Hess law is. So you're going to create that. You're going to create an energy cycle. So what are the steps involved? The first thing is you've got zinc and you've got iodine. You're going to break their bonds. So you're going to atomize them. You're going to turn them into atoms. So zinc gaseous atoms, and you're going to turn I2 into two iodine gaseous atoms. So you're breaking the iodine-iodine bond and you're breaking the metallic bonds in zinc. Is that clear? So that's atomization. Is that clear?
Yes, sir.
Then, because you're going to form the zinc iodide lattice, you have to ionize them. So you're going to turn zinc into a 2 plus gaseous ion, and you're going to turn iodine into -1 gaseous ions. So the next step is you're going to ionize them. And once those gaseous ions are formed, those gaseous ions will be brought together to form the ionic lattice, which is known as the lattice enthalpy. So once you have gaseous ions, you're going to form the ionic lattice. The ionic lattice is where you've got positive and negative ions all sticking together. That's what the ionic lattice is. So you did that in these three steps: atomize, ionize, and then form the lattice. Is that clear?
Yes, sir.
So all you have to do is you have to fill in the values for this, and we've got a table uh, on the other page. So we're going to use those. So first thing, enthalpy of formation of zinc iodide is that given. So delta H standard enthalpy change of formation of zinc iodide, that's minus 208. That's this value is provided, right? Then what else do I need? How do you turn zinc solid to zinc gaseous atoms? That's enthalpy change of atomization of zinc. So is this given in the question? It is given atomization of zinc. Atomization of zinc is that the zinc metallic solid turns into, you break all the bonds and it turns into atoms. So that is plus 131, right? So that is plus 131. Is that clear?
Yes, sir.
And I need to turn iodine solid into iodine gaseous atoms. How do I do that? So they gave me this, the enthalpy change, iodine solid to iodine gaseous. I said, now, they actually didn't give me this. What they gave me was, uh, so here's what I'm trying to do. I'm trying to turn iodine solid to iodine gaseous atoms, right? So I'm trying to find the enthalpy change for this one, iodine solid to two iodine gaseous atoms, right? Now I can't, based on the data that's given, I can't really reach this place in one go. I want to make iodine gaseous atoms, right? They've given me this thing. You can turn iodine solid to I2 gaseous atoms. So what I can do is I can turn I2 solid into I2 gaseous atoms, right? And that value is given as plus 62. And then they've given me the II bond energy as well, which is 151. So what I can do is I can break the II bond over here, the iodine-iodine bond, which is 151. And if I do that, I'm going to get two iodine gaseous atoms. So is that clear that I wanted this thing? I wanted iodine solid to turn into two iodine gaseous atoms, right? They gave me that I would have to first turn iodine solid into I2 gas, which is plus 62. And then I would have to break the iodine-iodine bond, and then I'll get the two iodine gaseous atoms. So it's plus 62 plus 151. Is this clear? This part?
Yes, sir.
So this thing over here, iodine solid to iodine, I would have to follow this path. I would have to first turn into I2 gas plus 62, then form this. So it's plus 62 plus 151. And then I have to ionize this. I have zinc and I'm going to turn it into 2 plus ions. So how do I do that? So it's the first ionization energy plus the second ionization energy. So that's plus 906 plus 1733, right? And then I want iodine to gain electrons, -1. I wanted to turn it into -1. That's electron affinity. And that is also should be given.
Multiply, do we multiply it by the mole number?
We're going to multiply it by, so that's the thing that we're actually trying to find. So we're going to multiply it by 2. I mean,
Okay.
he's asking you to figure out the electron affinity for iodine. So this is the path that we don't know. How do I turn iodine to I-1? I don't know, that's X. And since I'm doing it for 2, so I'm going to multiply it by 2. Is that clear?
Yes, sir.
And just one second. So the last thing is lattice energy. That's also given. The lattice energy is given as so what's the lattice energy that's over here? It's given as -2605. So this over here is also given -2605. So this is just a typical Born-Haber cycle where you had the enthalpy of formation of an ionic lattice. Then you did all the steps. You're going to atomize the elements, then you're going to ionize the elements, then the ions that are formed, you're going to bring them together to form the ionic lattice. That's lattice enthalpy. So we did all of that. We ionized zinc. Iodine turned into I-1. That's electron affinity. That's not known. Zinc solid turned to zinc gas. That's given as plus 131. I2 solid to 2I gas was tricky because I had to first, they gave me how to turn I2 solid into I2 gas. Then they also told me how to break the II bond. So I broke the bond and then I got two iodine gaseous atoms. Is this clear? So the cycle is complete. Is this clear?
Yes, sir.
And the Hess law is that one path is equal to the other path, right? So it's going to be -208, which should be equal to what? Plus 131, plus 62, plus 151, plus 906, plus 1733. Now try and do this as quickly as possible. And -2605. So I'm just going to do one. I'm going to take the 2x and I'm going to take it to the other side. So I'm going to put the 2x over here and I'm going to get the 208 to this side. And I'm going to divide the whole thing by -2 as well. So can you do?
Is it 1590?
So are you sure it's 1590?
1595.5.
This thing, right?
Yeah.
Let me check. I don't think that's the correct one. It's -293. Everything is exactly the same. Just make sure that as for to work this out, you got to be really good with your calculator. So I mean, even if the only thing I did was I got the 2x to the other side, so it became -2x. I got the -208 to the other side, so it became +208. And then
Okay, sir, got it.
-293.
Yeah, I forgot to subtract the 2605.
So just remember this calculation specifically. When you've got a lot of addition and subtractions going on, you have to be really careful with your calculator. It's very easy to mess this up. Now the next part is predict how the enthalpy, lattice enthalpy of CdI2 varies compared to Zn-I2. So that's the question. So no idea what. So lattice enthalpy. Lattice enthalpy is whoever makes the strongest lattice, that's going to be the more exothermic. Like what is lattice enthalpy? That you've got a bunch of gaseous ions. which are, so these ions are freely roaming around and they get together and they form the ionic lattice, right? That's what lattice enthalpy is. So whoever makes the strongest bond, it's going to have the high. It's going to have the more exothermic lattice enthalpy. Who's going to make the strongest bond? The one that have smaller ions with greater charge, which basically means greater charge density, right? Is that clear?
Yes, sir.
So the smaller the ion, the greater the charge on that ion, the stronger will be the lattice. So how do I know which one is so this cadmium CdI2 and ZnI2? So is there any information that is provided? Is there a period table? Just one second. So we've got a period table with us. So where exactly is cadmium? Um, Zinc is over here. Cadmium is below it. So who's the bigger ion out of the two? It's going to be
Uh, CD.
so it's going to be Cd, right? Is it all got upside down? Just a second. So it's going to be CD. CD is the bigger ion, so it's going to form the weaker lattice. So this one, you just have to mention that cadmium 2 plus ionic radius is bigger than Zn2 plus. Hence, it has a lower charge density. And because of that, because of this, it's not going to form very strong bonds. I mean, not strong, it's got a lower charge density, so it's going to form a weaker lattice. And hence, delta H lattice enthalpy will be less exothermic. Is that clear?
Yes, sir.
So now the next one, which is a different question. There's decomposition, and that's about Gibbs free energy. So it's about Gibbs free energy. It's about entropy change. And he's saying that these are the values of Gibbs free energy. So do you have any idea what Gibbs free energy is?
Yes, sir. I think I do.
So what is the formula for? I mean, what does delta G? What happens if delta G is positive, greater than 0? What happens if delta G is negative? Like, what's the significance of this?
Yeah, it actually shows how spontaneous our reaction is.
So this one is spontaneous, right? Negative, right?
Yes, sir.
So basically, Gibbs free energy is the total energy that is available for a system
Yes, sir.
to do useful work, right? It's delta G is basically the energy due to enthalpy change. So it's the energy that's due to delta S plus it's the energy due to entropy change, right? A system.
Yes, sir. Sir, I thought it's minus.
Hmm?
I thought it was minus and not plus. Change in system.
Nee, we just what is minus delta G?
No, delta G equals to energy. Uh, it's okay, sir. You explain because I'm kind of confused now.
Nee, the formula for delta G is delta H minus T delta S. That's the formula.
Yeah, that's what I was like asking. Yeah.
Nee, it's just that Sorry, this is not delta S. This energy due to delta H, right? Plus energy
Yes.
due to delta S. The thing is that this thing has an opposite sign, which means that it's not actually minus. I mean, it depends. It could be plus, it could be minus. It depends on the delta S value, right? Um, because if delta S is minus, then this thing would automatically become plus, right? Is that clear?
Yes, sir.
I'll just briefly explain that a system produces work in two ways. Like if you burn a match, heat energy is produced, right? That's enthalpy change. You burn petrol, heat energy is produced. But when you burn petrol, a lot of disorder is created, right? It's what happens is when you burn petrol, you got one molecule of octane, and all of a sudden, small molecules of carbon dioxide get produced, right? And there's a lot of disorder created. And when a lot of disorder is created, the piston starts moving upwards, right? So that is delta S positive, that a lot of disorder is being created, right? Whenever disorder is created, work gets produced. Like you burn a match, not a lot of disorder is created. But if you burn a firecracker, a lot of disorder is created, right? So whenever a lot of disorder is created, a lot of work gets produced. Is that idea clear?
Yes, sir.
So the piston would start to move upwards. I mean, steam engines, etc., they also work on the same concept. You turn water liquid into water gas, right? The gas will have a lot of disorder. It will create a lot of disorder. So gas molecules will push the piston upwards. So whenever delta S is positive, work gets produced. And if it's getting produced, it's going to have a negative sign. Is that clear?
Yes, sir.
So that's why you got a negative sign over here, that whenever delta S is positive, work gets produced. So how did we get this formula then? We got this formula because entropy change is basically the work that gets produced. So it's the, sorry, so it's the work, so it's the work that gets produced at a particular temperature in kelvins, right? I mean, you whenever disorder gets created, the piston will start moving upwards. And so work, a certain amount of work. If there is no disorder being created, the piston will stay wherever it is. Is that clear?
Yes, sir.
So it's the work that is produced, which has a negative sign because it's being produced when delta S is positive. So that's why they've got opposite signs at a particular temperature. So if I want to make work the subject of the equation, it's going to be work will be T times delta S. It's going to be minus T times delta S. I can rearrange the equation. The work that gets produced is basically minus T times delta S. So that's where we get, this is the work that's produced due to disorder. So Sina, is this clear, this equation for delta G?
Yes, sir.
So every time whenever a process happens, heat energy is either produced or consumed. But at the same time, due to disorder being created, the piston would start moving upwards. So there's going to be work that will be produced because of disorder. And that's minus T times delta S. And when delta G is negative, that means the reaction is spontaneous. That means it's an overall exothermic process. It means that the system does not need help from the outside. Is that clear as well?
Yes, sir.
And when delta G is greater than zero, it's positive. That means it's kind of endothermic. That means it needs your help. It needs some energy that should enter the system. Uh, and unless that energy is not added to the system, it's not going to work. So delta G greater than zero is kind of endothermic. Delta G less than zero is kind of exothermic, and that means it's going to be spontaneous, right? So that means this particular reaction is spontaneous over here. Is that clear?
Yes, sir.
And over here, it's not feasible. It's not spontaneous. It's not going to happen under these conditions. So he's asking you, I think, to plot these values, right? It's so plot delta G against T. So T is, so at 1050, it's 9.9. 1050, it's somewhere in between 9.9. Where's 9.9? I think I can only sketch over here. 1085, that's 4.3. 1080, what scale is this?
I'm sorry, sir, again.
So this one, 1085, that's this somewhere over here, 1085, that's 4.3.
9, 4. Oh
So
yeah, that's 4.3. Yes, sir. That's somewhere between 5 and 2.5.
okay, 1120, that's minus 1.3. So I guess
That's
it's
between.
so I guess it's going to be just a straight line. You can like sketch it on your own. He's going to ask you for the point at which the reaction becomes feasible. No, he's not actually. Calculate the gradient of your graph. Determine the delta S in joules per Kelvin per mole for this reaction, showing all the working. So determine the delta S in joules per Kelvin per mole for this reaction, showing all your working. Now, when does a reaction become feasible? Delta G is equal to what? It's equal to delta H minus T times delta S, right?
Yes, sir.
So, so what are you plotting? You're plotting T versus delta G, right? I mean, this
Yes,
graph.
sir.
Can you compare it with the equation of a straight line? Like delta G is your y-axis, and T over here is your x-axis, right? So, what do you think delta S is? Isn't this equation y is equal to mx plus c?
Yes, sir.
Because you've got two variables, you've got y and you've got x. You're plotting these two things. So m is the gradient, and the gradient is delta S. So you can calculate the gradient, whatever that comes out to be. It's I mean, we can kind of sketch it. It's y change in y. Let's say that's 11, right? So that's 11, and change in x. That's not really sure. 1040. So let's call it 80, right? So that's 80. So kilojoules, Kelvin. So delta S is going to be this gradient, right? It's going to be 11 over 80. Is that clear?
Yes, sir.
So is this idea clear? This question was slightly tricky because remember delta G is equal to delta H minus T delta S, and if you're plotting delta G versus T, this equation is kind of an equation of a straight line. Y is in the you get this part, right? Y is equal to mx plus c part. Is that part clear?
Yes, sir.
Okay, so uh, there could have been another way to calculate delta S as well, which was that what is delta G? Delta G is equal to delta H minus T delta S. Actually, there was no other way because I don't think they gave us delta H as well. Did they? They did. Uh, no. So there is no other way because you don't have delta H. All you had was this graph, and all you had was that you were supposed to compare it with the equation of a straight line. So if it was y against x, then m was the gradient, which was delta S over here. So anyways, the next question is write an ionic equation for the thermal decomposition of the hydrogen carbonate ion. So what will it decompose into? It's going to decompose into carbon dioxide, and it's going to produce what is it going to produce? Sorry, carbonate ion, and he gave the question above. He's saying that there is, as he gave the whole equation, there was M8CO3, and on general heating, it would decompose into a metal carbonate, which would be M2CO3. M, remember, is plus one over here, so this is minus two, so there's going to be two of them. And carbon dioxide and water vapor. The Ionic equation is you just get rid of the M. So there were two M's over here, just get rid of the M. So you're getting a carbonate ion, you're getting carbon dioxide, and you're getting water as well. And this equation kind of looks balanced. So we just remove the metal ion from the equation. Is this clear?
Sir.
Yeah.
Yeah. That's clear with me.
Okay, and this is actually minus one. Remember, HCO3 is actually -1. So M was +1. I figured this out because HCO3 is -1, so M is +1. So there was an M +1, there was an M +1 over here as well. We just got rid of that. Now,
Sir, is this fixed?
is this?
Is this equation fixed or no?
It's you just had to guess the equation from. I mean, this is not in your course. I mean, this equation is not in your syllabus. They
All right.
gave, they gave everything over here that there was an M8CO3, right? So there was an so it was M +1 HCO3 -1, and it was forming a metal carbonate. Now you knew that M was +1, right? So the formula of this thing will be the metal carbonate would be M2CO3, right? And it was
Yes,
producing,
sir.
and that's why I wrote 2 over here because there were 2 M's over here in this formula, so there should be 2 MHCO3, right? And there was CO2 and water vapor also getting formed. So all I did was got rid of him, right?
Okay, sir.
Because
Yes, sir.
he was only looking for the ionic equation for the decomposition of the hydrogen carbonate ion. Now the next part is why does the thermal stability increase down the group? What do you think? Why does this thermal stability increase down the group? Like if you have MgCO3, like you've got, let's say you've got a carbonate ion, right? And there's a magnesium ion. Magnesium ions are small in size. And there's another carbonate down the group. So the carbonate ion is the same. So the carbonate ion is not a factor. It's the same. It's in barium carbonate, it's going to be the same. Now barium is going to be a bigger ion, right? So what happens down the group? The difference between MgCO3 is very unstable. Barium carbonate is highly stable. So this one is stable, and the top one is unstable. It decomposes easily. That's what the question is stating as well. That the stability increases down the group, right? So we need to figure out and find the reason. Now the only thing that's changing is the ionic radius, right?
Yes, sir.
It increases. What happens to the charge density? It decreases.
Decreases.
So the charge density of the cation decreases. So stronger attraction or weaker attraction if you have a lower charge density. Hmm?
Low charge density, sir?
I mean,
Weaker attraction?
so there's going to be a weaker. I mean, so this one is going to be weaker attraction, right? This one over here is going to be a lot stronger attraction, right? So
Yes, sir.
why is the first one more unstable, even though there's a stronger attraction between the two? I mean, the first one has stronger attraction, so it's supposed to form stronger bonds, right?
Yes, sir.
But what happens is that the attraction is so strong that the carbonate ion becomes polarized. The oxygen and its electrons, they get pulled towards the magnesium and they end up forming magnesium oxide, and the carbon dioxide is left behind. Is that idea clear? Because the attraction is so strong.
Yes, sir.
So smaller ions will polarize the carbonate ions. Or in this case, he's talking about hydrogen carbonate, so it will polarize the hydrogen carbonate ion, making it unstable. So that makes it extremely unstable. So that's about that. And remember, this one is a very typical question as well. That what happens? Why does the stability increase down the group? So it's a very typical question where you have to answer that. You got a smaller end. Smaller ends have greater charge density, and therefore they have a higher polarizing power. And they're going to polarize the bonds in the carbonate ion. Right? Is this clear?
Yes, sir.
Now the other part is define a buffer. Do you know what a buffer is?
Yes, sir.
What is it? How do you define it?
Um, as, as far as I remember, buffer helps with the pH, the change in pH.
So it resists a change in pH. It doesn't allow a change in pH. When what happens? When a small amount of acid, when a small amount of acid or alkali is added to it, right? Is that clear?
Yes, sir.
So when a small amount of acid or alkali is added to it, so it's not going to resist a change. It's going to resist a change in pH. It's usually formed when you have a weak acid plus its conjugate base as well. So he's asking about two equations for the buffer. So here's the idea of what a buffer is. Uh, that you've got a weak acid. What does a weak acid do? Let's say you've got a weak acid, right? Now H2CO3 is the weak acid. What does it do? It's going to an acid produces H plus ions, right?
Yes, sir.
So what a weak acid will do is that
Partially.
that when it sees OH ions, I mean it's not going to ionize it. A weak acid doesn't really ionize a lot, right? But when it sees OH ions, because OH ions are negatively charged, the H plus one will get attracted to the OH ions and they're going to neutralize it. The H plus one from the acid. So remember, an acid which is weak will not release a lot of H plus one ions. But if there's an OH ion present, the OH ion is negatively charged, so the OH ion will attract those H plus one ions. So the acid will start to ionize. Is that idea clear?
Yes, sir.
You remove the OH ions, the weak acid will not ionize. You put in the OH ions, the weak acid will start to produce a lot of H plus one ions. And those H plus one ions are going to go and they're going to neutralize the OH ions, and they will get attracted to the OH ions. What's going to be left behind is HCO3 minus one. Is that clear?
Yes, sir.
So now a buffer is something that if you add OH ions, right, it's going to immediately neutralize them. So which is why you need a weak acid in the solution. That as soon as somebody adds OH ions into the solution, it quickly neutralizes those OH ions. And remember, what is pH like? What's the story behind pH? It's that everything is happening in a solution, right? Everything is kind of so. I mean, all those particles around you are swimming around in water. So there's water everywhere, and water produces two ions. One is H plus one. The other one is OH ion. So when you have all the particles like in your body, in your blood cells, the red blood cells and the white blood cells, and all the reactions that are happening in the stomach, okay? So all these particles are roaming around in a solution that's made up of water, and water has H plus one and OH ions. Now, H plus one and OH ions are usually in the same quantity if the water is neutral. If you add an acid, what does an acid do? It increases the quantity of H plus one and decreases the quantity of OH ions because the acid likes to produce H plus ions. A strong acid will produce a lot of H plus ions. If you add a base, the base will do the opposite. It will decrease the quantity of H plus one and increase the quantity of OH ions. Is that clear?
Yes, sir. Sir, can you please repeat this part again?
See, everything, all the reactions on planet Earth, pretty much are happening in water. Water is the main medium, right? Like the human body is mostly water. It's mostly water, right?
Mhm.
So so what happens is that water. So all these particles that you see, the plants. How do the plants absorb all the minerals and compounds and salts, etc.? They all absorb them through water, right? They're always you stop giving them water, the reaction stops because these particles are not able to move around without water. Like, how does my body transport oxygen to all my cells? It transports it through my blood, right? And the blood is water basically. So do you get the idea that why water is so important, right?
Yes, sir.
And water breaks down, you know that, right? Water ionizes and produces two ions. One is H+1, the other one is OH ions, right?
Yes, sir.
Now, normally the quantity of H+1 and OH ions would be exactly the same because one water molecule, if it ionizes, it will produce the same H+1 and OH ions. Like it's going to produce one H+1 and one OH ions, right? So it's going to produce them in equal quantity, right? That's called a neutral solution. Now, if I add a molecule of acid to it, so let's say this is a molecule of acid. What does an acid do? It likes to release H+1 ions. A strong acid will release a lot of H+1 ions, right? So what will happen to the quantity of H+1 ions in the solution? It's going to increase, right?
Yes, sir.
That's known as that the solution has become acidic. Like your stomach is acidic. So that's the reason why it's acidic. Vice versa, if you add a base to it, what does a base do? The base accepts like these oxides and hydroxides, they attract H+1 ions and they consume the H+1 ions. So the solution will have fewer H+1 ions. So you'll say that the solution has now turned basic, right? Is that clear?
Yes, sir.
Now, the green particles over here, like all your red blood cells and your white blood cells and your platelets and your all the reactions that are happening in the stomach, they don't like any disturbance in the balance. Like some reactions would prefer that the solution has more H+1 ions. Some reactions would prefer that the solution has more OH ions, right? Like all the reactions that are going on in your stomach, they would prefer what? More H+1 or more OH ions?
More OH, sir?
Is your stomach acidic or basic?
Oh, wait, no, I mean acidic, so more H plus ions.
So that means all the reactions that are happening, the digestive reactions, etc. They probably need H+1 ions. That's why they prefer more H+1 ions, right? Some reactions would require more OH ions, so they would prefer basic conditions. Some of them would either not require any H+1 or OH ions, so they would prefer neutral conditions, like they don't really care about H+1 or OH ions, or maybe they would need H+1 and OH ions in equal quantity, right? So so remember, reactions, they get disturbed if you change the balance of the solution. If you alter the pH, if you alter the balance between H+1 and OH ions, the reactions, they get disturbed. Your stomach reactions will stop happening if you don't provide them with H+1 ions. Or if you add too many OH ions into the stomach, the reactions will stop. Is that idea clear?
Yes, sir.
So the logic is that every natural system is naturally a buffer solution, that they try to resist changes in pH, right? So if I try to add more OH ions into a solution, so a buffer solution will have a weak acid. Like the moment I try to add OH ions, the weak acid will start producing H+1 ions and it will neutralize the OH ions. Is that idea clear?
Yes, sir.
So it doesn't allow you to actually increase the H+1 ions, OH ions. Vice versa, you would need a conjugate base as well. This is the conjugate base. The conjugate base is formed when the acid ionizes. So you would need these ions as well, because if somebody tries to add too many H+1 ions, the negative ion will attract the H+1 ions and will absorb those H+1 ions, forming H2CO3 back again. Is that clear?
Yes, sir.
So that's the conjugate base of the weak acid. So a buffer is formed when you add two things together. You add a weak acid. The weak acid will not do anything initially because it doesn't like to ionize. But if you add too many OH ions, it will quickly go and neutralize the extra OH ions. Vice versa, if the solution should also have the conjugate base, which is the reverse, that if you add too many H plus one ions, then the conjugate base will, and remember, you have the idea, right, that HCl is an acid. When it ionizes, it forms the conjugate base. Like in the forward direction, as it acts as an acid because it produces H+1 ions. In the reverse direction, Cl minus one gains the H+1, so it's a base. Is that idea clear? Asina, is this clear?
Yes, sir.
Okay, so we're going to do this question. We're going to talk about, but get this idea clear that acids and bases, we don't want, every reaction has a certain preference. And they would prefer the solution to be at a certain pH. Some would prefer acidic, some would prefer basic, some would prefer neutral. And the pH should not change. The balance of H+1 and OH ions should not change. And that's what the buffer does. So he was asking to construct two equations, and we did just that. That a buffer will have a weak acid, which is H2CO3 in this case. It will neutralize any OH ion that comes in. It's going to provide H+1 ions and neutralize it. And a buffer will also have the conjugate base. That if somebody adds too many H+1 ions into the solution, the conjugate base will absorb all of them. And it will neutralize these as well. So it will prevent the acid or the solution from becoming too alkaline or too acidic. Is that clear? Asira, I can't hear you actually. I'm not really sure. Hello?
Sir, can you hear me now?
Yes. So is this clear? Just this idea. We'll do this question next time, but we can have a class tomorrow as well at it's felt good for you. I mean, you can just message me on WhatsApp.
Okay, sir. By the way, sir, is there a way I can access this recording?
Yes, you can. I'll share the recordings. I'll share the folder with you.
Okay, thank you so much, sir.
Okay, take care. Bye bye.
Okay, thank you, sir. Bye. Good night.